Let us begin with the proof of Taylor's theorem. Let me quickly write down the theorem also. Taylor's theorem. अजून येत आहेत ना आपले गेस्ट. थंडी वाढल्यामुळे हँडरायटिंग बिघडलेलं आहे. Anyway, let f is defined from a to x to r. If 1 n minus 1th derivative exists and is continuous. On closed interval a comma x to fn exists on open interval a comma x, then 3 there exists c belonging to open interval a comma x such that f of x is equal to f of a plus first derivative evaluated at a upon 1 factorial x minus a raised to 1 plus second derivative evaluated at a upon 2 factorial into x minus a raised to 2 plus dot 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 plus n minus 1th derivative evaluated at a divided by n minus 1 factorial into x minus a raised to n minus 1 plus nth derivative evaluated at c divided by n factorial into x minus a raised to n. Full stop. This was our theorem. Let us write down the proof. The first step of the proof was define g, function g, such that it is defined on a to x to r. G of t is equal to f of t plus first derivative evaluated at t divided by 1 factorial into x minus raised to 1 plus second derivative evaluated at t by 2 factorial into x minus t raised to 2 plus dot 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 plus n minus 1th derivative evaluated at t divided by n minus 1 factorial into x minus t raised to n minus 1 plus constant a times x minus t raised to n. Note g of 0 g of a is equal to f of a plus f dash of a upon 1 factorial into x minus a. It is exactly similar to f of x, except this constant, it is exactly similar. So if we do not know this statement of this theorem and we write some constant here, then these two statements are same, and therefore f of a is equal to g of a is equal to f of x and g of x, if we substitute, then every term after this is 0, which is equal to f of x. Hence, Rolle's theorem is applicable. Okay, so if Rolle's theorem is applicable, then Rolle's theorem says there exists C such that g dash of C is equal to 0. Therefore, g dash of t is equal to, first differentiate this and then put C. Okay. So if we differentiate g dash of t, that is the only critical thing. With respect to t, we are supposed to differentiate. So if we differentiate first term, it will be f dash of t plus, if we differentiate second term, keeping, this is the product of two terms, therefore keeping second term constant, we get second derivative evaluated at t upon 1 factorial into x minus t raised to 1 plus, now I will not write plus because this derivative of this is going to be minus 1 and this term as it is. So it will be minus first derivative evaluated at t upon 1 factorial into derivative of this, which is minus 1, which is taken care, plus second term if we differentiate. Third derivative evaluated at t बरोबर चाललंय. Third derivative evaluated at t upon 2 factorial into x minus t bracket square plus परत एकदा मायनस होईल आणि मग सेकंड डेरिव्हेटिव्ह evaluated at t upon 2 factorial into sorry, याचं काय डेरिव्हेटिव्ह येणार आहे 2 into x minus t, 2 into x minus t into minus 1. बरोबर चाललंय. Do you see there is a cancellation of this term is produced here. This term is getting cancelled here. So now this term is surviving, which will get cancelled later on. So what should I do? I should write down the derivative of n minus 1th term now. Okay. So derivative of n minus 1th term will be plus dot 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 plus then n evaluated at t upon n minus 1 factorial into x minus t raised to n minus 1 plus minus f n minus 1 evaluated at t upon n minus 1 factorial, and then derivative of that is n minus 1 into x raised minus t raised to n minus 2 into minus 1. I am done with it, and then I am supposed to differentiate the last term, which is plus a n x minus t raised to n minus 1 with minus sign. Okay, let me take a pause and check whether everything I have written is correct or not, and secondly whether you have understood this or not. So any questions or any mistake in my writing? कहाँ आवाज येतोय एवढा? Correct है? Good. Okay. So can you now tell me what is remaining after lot of cancellation? After lot of cancellation, g dash of t, this implies g dash of t is equal to one term with a negative sign. This term will get cancelled, I think. This term will survive because this term does not have anybody else afterwards to get cancelled, because this is what it's supposed to be cancelling this, but this is not the same term. Therefore, this term will survive and this term will survive. Okay, everything else will get cancelled. So what do we have now? Nth derivative evaluated at t upon n minus 1 factorial into x minus t raised to n minus 1 minus a times n times x minus t raised to n minus 1. And now we are supposed to put t is equal to c and say that it is equal to 0. So putting t is equal to c and equating it to 0, we get this is equal to this. So let us write down f nth derivative evaluated at c upon n minus 1 factorial is equal to into x minus c raised to n minus 1 is equal to a n x minus c raised to n minus 1. So this x minus c raised to n minus 1 gets cancelled because it is not equal to 0, and therefore you get this n transposed to the other side and you get a is equal to fn evaluated at c upon n factorial. That is the beauty of this theorem. You get exactly the thing that you want. Now, why is this theorem so important, or maybe this is generalized theorem? Because if we consider the statement of this theorem, where is it? This theorem here. And if we say we are not interested in n, let us take n is equal to 1. First derivative, we are okay with first derivative. Right? Then what will happen? What will happen? I am not interested in n plus 1 higher terms. Let us write n is equal to 1. In that case, the special case of this theorem, Taylor's expansion, if I write it for n is equal to 1, it will be f of x is equal to f of a plus f dash evaluated at c. This is the term that I am writing now, upon 1 factorial into x minus a raised to 1. And if we simplify this, we get f of x minus f of a upon x minus a is equal to f dash of c. So this is LMVT. Lagrangian mean value theorem happens to be special case of Taylor's theorem. That is why it is important. So Lagrangian mean value theorem talks about only first derivative and stop, and then still they are equal. Still they are equal. You will find one line, one tangent. If the function is continuous, you will find one tangent whose slope is equal to slope of the chord. Geometrically, this is easy to visualize, LMVT. Okay, but then you are stopping at first derivative, therefore it is less correct. Less correct means error percentage is more. If you take higher order derivatives and if you stretch yourself little bit, then you are going to get more accurate approximation. Okay. Now, question in everybody's mind is, after doing so, will we be able to find out this term? Will we be able to find out the value of the remainder term? This is our remainder term, which is something which we are adding from our pocket to get the equality of these two things. F of x is any function, not necessarily polynomial function, but it can be written as polynomial looking function provided you are able to control the remainder. Find out and check whether it is convergent or not. This is the theory which we need to understand. What do we mean by this remainder? If remainder is not there, then RHS is not equal to LHS. It is approximately equal. For all practical purposes, it will be equal if you take more number of terms and the function is convergent. But if the function is oscillating or divergent, the approximation of a function by polynomial function may not be correct. And therefore, this remainder term that we have found out using this is extremely important. And you need to work on this to figure out whether your function will behave like polynomial or not. So remainder term is important now. Okay. So I put the entire proof on the board. Wait for a couple of minutes before we start really checking the functions that we have found out, like sin x, cos x, log 1 plus x, e raised to x, whether they are legal. The expansions that we have done, are they legal? Are they authentic? Will they work or not? Okay, now let us consider the signs we have developed. F of x is equal to sin x. What is f n of x? Nth derivative of this function, it is sin x plus n pi by 2. Correct? That is what is your nth derivative. So now what are we supposed to check? What is our remainder term? Our remainder term is Rn. Nth remainder term is basically function of. It will be dependent on A, the base point. The remainder term will depend on where your position of x is, and it will be dependent on the function. So remainder term is dependent on, so I should not use f 2 times. Remainder term is dependent on the function, the value of your base point, and the right hand limit. In case of a comma x, the right hand limit, it is dependent on these three parameters. So g of this dependent on this. So as far as Taylor's theorem is concerned, our remainder term Rn is nth derivative of f evaluated at c upon n factorial into x minus a raised to n. This is our remainder term as per Taylor. Okay. So we need to now figure, as n tends to infinity, limit as n tends to infinity. If we keep differentiating, then we need to find out limit as n tends to infinity sin c plus n pi by 2, and we are taking a is equal to 0, suppose, divided by n factorial. Near 0 we are studying, so it will be x raised to n. What is the future of this limit. If we could evaluate that, then we will be able to successfully say that the series expansion of sin x, whatever we have written couple of lectures before, is legal and we can use it. So now your job is to find this limit and show it to me. What is the procedure by which you will be able to evaluate this limit as n tends to infinity? This is x raised to n tends to infinity. X is the right hand limit of your interval on which this f is defined. Okay, so I give you sufficient time to find out that limit. Okay, so when it comes to evaluation of this limit, which is limit n tends to infinity sin c plus n pi by 2 upon n factorial into x raised to n, we are aware that sine of whatever quantity is a bounded function and will have value between -1 to 1. So it is not trouble causing element over here as far as this function is concerned, this term is concerned. Therefore, we can split this limit in two parts. Limit n tends to infinity sine c plus n pi by 2 into x raised to n upon n factorial. Okay, so we provided a limit of this exists and is finite, we can apply product rule to these two terms, these two functions, and evaluate this limit. However, this is simple because it is finite and between -1 to 1. So the challenge is to evaluate limit n tends to infinity x raised to n upon n factorial. So if you write them separately, then there are infinitely many terms, and hence you cannot use product of limit is equal to limit of product for infinitely many terms. It is true for finitely many terms. Therefore, we will have to do something else. So let us take this function separately and deal with it, and then take limit as n tends to infinity. What is this? X raised to n upon n factorial. Who is more powerful? X is a fixed finite number, one number line. We don't know. It might be a big number, but it is a finite. It is not tending to, x is not tending to infinity. N is tending to infinity. Therefore, we can visualize this as x into x into x into dot 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 x. How many? N times divided by 1 into 2 into 3 dot 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 n. So total number of terms in the numerator and in the denominator, they are same. That is good part of it. X raised to n, x getting multiplied to each other n times, n factorial 1 2 3 4 up to n, all these terms. Now if we imagine this number, suppose we consider that x is equal to 100. Okay, so for example, x is equal to 100. So we have this ratio as 100 upon 1 into 100 upon 2. We give each to each. Okay, so 100 upon 2 dot dot dot, we will reach 100 upon 99 into 100 upon 100 into 100 upon 101 and so on. Okay, so for a fixed finite number x, not necessarily integer, but whatever is that, there will be first k terms up to k, there will be k terms which will produce the fraction which is greater than 1, and k plus 1th term will be the fraction less than 1 and so on. Do you all agree with this? So for this, what we can write is, this is x upon 1 into x upon 2 dot 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 x upon n. This is what we have. So if we consider this explanation for x is equal to 100, I can write it in terms of x looking like this is equal to. Understand this what? I am going into the details of what are those fractions. So I can write it as, I can create a bracket in which I can put x upon 1 into x upon 2 into dot dot dot. Okay, when it was 100, this was 100. What do I put in the denominator now? X upon, we have a function, this. This is the smallest, smaller but greatest integer than x. Now this fraction is the last fraction which is going to be greater than 1, and then all the fractions after that will look like greatest integer x plus 1 into x upon greatest integer x plus 2, sorry, dot dot dot. Okay, what will be the last bracket? Sanga, x upon greatest integer x plus, bola, what should I write in the end?
n minus greatest integer x.
N minus greatest integer x, because we want x upon n in the end. These are the total number of terms which we have written here. Okay. Now this is the number which is greater than product of numbers which are greater than 1. Okay. You can call it as a big number, say k. K is a product of this. And then what comes next is product of all of them, and product of all of them, denominator of each of these brackets is bigger, therefore they are these, I mean this bracket is smaller than this bracket, this bracket is smaller than this bracket. Okay, so if I replace all the brackets after the first bracket by first bracket, I am creating inequality which is of the kind less than, strictly less than. Do you agree? And then I am writing x upon greatest integer x plus 1. How many times? How many brackets are there total? N minus greatest integer x. These many brackets are there. Strict inequality less than. Understand this. Okay. Now, this is definitely a fraction and is less than 1. Note, x upon greatest integer x plus 1 is greater than 0 and less than 1. So we consider this equal to k times t raised to n minus greatest integer x, where t is equal to x upon greatest integer x plus 1. Again, t is a number, t is a fraction which is less than 1. So k into t raised to n upon t raised to greatest integer x. Now t raised to greatest integer x is yet another number. So this is k dash t raised to n. That is where we have arrived at, where t is less than 1. And now if we take limit of this, that is going to be equal to limit of n tends to infinity k dash t raised to n, as n tends to infinity t is less than 0. Answer is 0. Check whether you have understood. Break it up into the final details. Now you need to visualize this number example for 100, x is equal to 100. What will happen? Doesn't matter whether x is 100 or 1 lakh or 5 lakhs or 10 lakh, doesn't matter. So far it is a finite number. We always have a proof with us because n is tending to infinity. It is going to grow. N is larger than any finite number that you can imagine. Okay, so I am keeping this entire proof again on board, waiting for a couple of minutes. So this is where we can declare that as the remainder term, Taylor's remainder, as n tends to infinity becomes 0, sine series is legal series and we can use it. Higher number of terms you take, you will get better and better accuracy. So next job is to legalize cos, but then you will find that it is exactly the same proof because except this term, everything is going to be the same as far as remainder is concerned. So let me announce sine and cos are legal. Hence, series expansion. More number of terms will give better accuracy. Okay, next we have to legalize is check f of x is equal to e raised to x. Okay, so you have to write down remainder term, take the limit and show that that is also convergent. This is easy because e raised to c, the nth derivative evaluated at c is e raised to c, and again the next term is same x raised to, so Rn is equal to e raised to c x raised to n upon n factorial. Okay, so limit Rn as n tends to infinity limit e raised to c x raised to n upon n factorial. Okay, and what is so good about c is our base point is 0 is less than c is less than x, right? E is greater than 0, therefore e raised to 0 is less than बरोबर लिहिलं माझ्याकडे उलट का लिहिलेलं आहे बरोबर आहे okay so if this is true then e raised to 0 x raised to n upon n factorial is less than e raised to c x raised to n upon n factorial less than e raised to x x raised to n upon n factorial, and taking limit or limit of this is 1, therefore limit of this and limit of this using sandwich theorem, limit of this tends to this one and the same. Or you can directly say here that this is fixed. Finite number multiplied by 0 is 0, and therefore this limit goes to 0. Check. Next problem is check for log to the base e 1 plus x. Okay, so this is not going to be that easy. First of all, you have to find out nth derivative. Secondly, what is the domain of definition of this function, because it is log 1 plus x. So x can start little more than minus 1 and can tend to plus infinity. Less than minus 1 or equal to minus 1, value of x is not acceptable. So domain of definition of f of x is open interval minus 1 to plus infinity. And now if you keep looking at this interval, x can take values between minus 1 to plus infinity, you might be in trouble as far as that remainder is concerned. So then split that remainder into the convenient parts that you want to split, and then confirm that it is convergent for this and then divergent for this, and then we are not able to find out for this part of the domain, etc. So you break that domain in parts and report, try to report your answer. It might not be the correct series for any x, it might be correct series for some x. Okay, so you should not get afraid of that. You can deliver whatever best you can. We want it to be convergent, and you can report that yes, it is convergent between this to this, and not necessarily convergent beyond this. Something like that you can report. Now let me write down the remainder term first. The remainder term in case of this Rn, in case of log 1 plus x, the remainder is minus 1 raised to n minus 1 into x raised to n upon n into 1 plus c raised to n. First of all, you need to agree with this, that this is the remainder term. Now x can vary between minus 1 to plus infinity. Okay, so if x is greater than 1, then what will happen? If x is greater than 1, now let us keep this minus 1 upon raised to n minus 1 upon n aside and look at x upon 1 plus c raised to n. Okay, so eventually what you are trying to say, all of you are minus 1 raised to n minus 1 upon n, and as n tends to infinity you would like to see this as 0, but it depends on whether this is 0 or not. So we are keeping this factor aside and considering only this. So if x is greater than 1, so this is the picture now, this is 0, this is 1, and you are considering values of x greater than 1, but c can be between, c is, how is c? 0 is less than c is less than x. That is the condition on c. Therefore c can be between 0 to 1. When x is greater than 1, that means this ratio x upon 1 plus x is 1 plus c can become greater than 1. And anything greater than 1 raised to n, which is tending to infinity, is divergent. Correct? And therefore, this series that we have developed for log 1 plus x is not going to be behaving well if x value is greater than 1 for sure. So we cannot use it for this interval. We cannot use it. Okay. Now let us see if x belongs to say 0 to 1. So if x is between 0 to 1, that is 0 is less than x is less than 1, then c is between 0 is less than c is less than x. Then what will happen? This x upon 1 plus c, x upon 1 plus c, x upon 1 plus c is going to be greater than 0, but definitely less than 1. Because x can be maximum 1 and denominator is going to be greater than 1. Therefore, this fraction is less than 1 and positive. Therefore, this bracket is going to tend to 0 as n tends to infinity. And anyway, this ratio is going to tend to 0 as n tends to infinity, convergent. So we can use it. Okay, so now which particular zone is pending? The number of values of x which are pending if x belongs to -1 to 0. Okay, now if x belongs to -1 to 0, that means -1 is less than x is less than 0 and c is between 0 to x. 0 is less than c is less than x. No, x is not greater than 0. So this is not correct. X is less than c is less than 0. That is what is the situation. So in this case, is this fraction between 0 to 1, then it is convergent, else not. So let us take x is equal to -0.8. For example, x is equal to -0.8 and c is equal to -0.5. Then -0.8 upon 1 plus -0.5 is equal to 0.8 upon 0.5, which is greater than 1. No. Which is not greater than 1, I cannot directly write it greater than 1, which is equal to -1 times something which is greater than 1. K is positive and is greater than 1, -1 times k. And then doesn't matter whether it is minus or plus, but if you take higher powers of this ratio, then it is not going to be convergent, so divergent. So even if one case fails, then we cannot say that it is always convergent. Understand this. Here it is always going to be convergent. Here if you take we are creating a counter example where it is not in control and divergent. Okay, so if it is divergent, we cannot use. So as far as this remainder is concerned, which is Taylor's remainder. Taylor's remainder approves log 1 plus x only for values of x belonging to 0 to 1. However, it is not true because we can always use it for minus 1 to 0, but then Taylor's remainder fails to prove that. Okay, therefore, few more mathematicians worked out their own remainders. And the second remainder term, I am not getting into derivation of Cauchy's remainder, where we will use Cauchy's mean value theorem, but Cauchy's remainder is like looking like this, remainder by Cauchy. So remainder by Cauchy's looks like Rn is equal to nth derivative evaluated at C divided by n minus 1 factorial into x minus c raised to n minus 1 into x minus a. Okay, now this is direct. I mean, we can write a derivation by which we get this remainder, but right now I am not getting into it because we have already proved the Taylor's remainder. So if you assume some other function, if you use Cauchy's mean value theorem, then you can arrive at this remainder. I mean, doing similar calculations, there also you get to have a lot of cancellation f and g, two functions, and eventually you end up getting this as your remainder. And now, if I give you this as Cauchy's remainder, can you prove that log 1 plus x is log 1 plus x, for log 1 plus x, Rn is convergent between, for x belonging to minus 1 to 0. So Cauchy's will permit you to use it for minus 1 to 0. Taylor will permit you to use it from 0 to 1, and hence log 1 plus x expansion series is okay for minus 1 to 1, x belonging to minus. This is what is the final result that we will remember. Okay, so what is pending with you now is, if this is the remainder by Cauchy, you have to prove that nth derivative evaluated at C of this function log 1 plus x is convergent between minus 1 to 0. And it is doable. Do it. Okay, so let us look at this remainder now. Basically, our base point is 0, so a is equal to 0. So f of chi plus Rn is going to be equal to minus 1 raised to n minus 1 upon n factorial into 1 plus c raised to n into x minus c raised to n minus 1 into x. This is what is your term, and basically what we are looking at is, now if x belongs to this, the relationship that we have is minus 1 is less than x is less than c is less than 0. Okay, So we need not have to worry about this x because it does not have any power. We need not have to worry about this minus 1 raised to n minus 1 upon n factorial also. We have to worry about this. So x minus c raised to n minus 1 upon 1 plus c raised to n. So what we can do is again 1 minus, it is x minus c upon 1 plus c raised to n into 1 upon x minus c. Okay, so x minus c is again, this is going to be a finite value. So we need to just look at this limit, and x minus c upon 1 plus c, this fraction is going to be less than, the absolute value of this fraction is going to be less than 1. Is it correct? X minus c upon 1 plus c. 1 plus c, are you there? I mean, this is going to be this bracket. Mod of x minus c upon 1 plus c is between 0 to 1. And if we take higher power of that, it is convergent. Right? Therefore, log इथे भी हा क्लोज्ड इंटरवल लिहिलेत त्याच्याऐवजी ते ओपन इंटरवल -1 ला नाही चालणार कारण तो 0 होईल. सो log 1 plus x is okay for x belonging to open interval -1 to closed interval +1. This is approved. Okay, so these are the, okay, one more function we need to try is our simple, because we have been using it. Another function that we must try is f of x is equal to 1 plus x raised to alpha, where alpha belongs to R. You need to cross check whether this works or not. Find the remainder term of this function and check the convergence.
So the n factorial term will get cancelled in the previous one, right?
Here?
Yes, sir. So because in the numerator we have n minus 1 factorial.
So only n will survive, I think. Yes.
No, sir. Even
N,
n will not be.
n minus 1 factorial is there na, in the numerator? No.
Yes, sir. And in the Rn formula also we have n minus 1 factorial.
Okay. So this term is not there, n factorial?
No, sir.
Sure. Then it is written in my notes. बाकीच्यांनी confirm करा that n factorial which I have written is correct or wrong?
Sir, Harshita is right.
This n factorial has to be there, na?
No, sir.
No? We have to delete it. Okay, later on I will cross check. Doubtful. Okay, so now the job with you is f of x is equal to 1 plus x raised to alpha, where alpha is a real number. Okay, so if you really write down the remainder term, Taylor's remainder term of this Rn, it will be looking like alpha into alpha minus 1 into alpha minus 2 dot 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 into alpha minus n plus 1 into 1 plus c raised to alpha upon n factorial into x upon 1 plus c bracket raised to n. Check. I mean, I am not getting into details how we have arrived this, but it is easy. Okay. And then this is something similar to your log 1 plus x also. We got exactly the same. So their condition was, again we have to write down Cauchy's remainder for this, because this will work only between 0 to 1, maybe 1 inclusive. It will work and not work beyond that. And if we want negative side, we have to write down Cauchy's remainder, and then it will work from minus 1 less than equal to x less than equal to 0. Then this is by Taylor, this is by Cauchy's, and hence this series is going to work, expansion of this is going to work for mod x less than 1, less than or equal to 1. That is the condition. So this expansion series will work if it is a real number alpha, will work for mod x less than or equal to 1, which we can prove using Taylor's remainder for 0 to 1 and Cauchy's remainder from minus 1 to 0. They are exactly the same term, so we did not have to write it is going to be exactly similar to log 1 plus x. Okay, so therefore we have legalized all possible easy power series expansions of a basic function sine cos, then e raised to x, a raised to x, 1 plus x raised to alpha log 1 plus x, and maybe tan inverse x also will have to legalize, but we are not getting into proving every remainder. So you can remember these many series expansions which will be very useful to you. Sometimes this is the only way to evaluate the limit, otherwise the limit evaluation becomes difficult. So series expansion of these basic functions you have to remember and use whenever you get a chance to use them, and they are legal. In the domain of definition where we have proved them to be legal, you can always use them. Okay, so that is where we are going to stop for the day. If there are any questions, you can ask.